Okay, we're ready for our fourth problem in this series. So the problem here is 25 minus x squared and then take the absolute value. So let's try to find a derivative of this one here. Well, the first thing to notice is that 25 minus x squared is actually a piecewise defined function. Well, the absolute value makes it a piecewise defined function. And so that is 25 minus x squared when the 25 minus x squared is greater than or equal to 0, and it's the opposite of that, which would be x squared minus 25, when the 25 minus x squared is less than 0. Okay, so from there we can use the piecewise defined function then to find the derivative. So the derivative of that is going to be the derivative of just these pieces here. And of course the derivative of 25 is 0. The derivative here, you bring the 2 down and this goes away, and here you bring the 2 down and this goes to the first power, and the derivative of the 25 there is 0. So we get that. Okay, and maybe I should rewrite this condition here. This is going to be add x squared to both sides. We get, maybe I should write it this way, x squared is less than or equal to 25. And this is x squared greater than 25. Which another way to say that is absolute value of x is less than 5. Or equal to. And of course this one would be absolute value of x greater than 5. Okay, so if I use that condition, I could use that as the conditions here. Okay, so that's the derivative, and then from there we can do the second derivative. Okay, actually, take this back. Notice that if x equals 5 or negative 5, these don't match. So actually, this derivative has the original function has a sharp corner there. So the derivative is actually undefined at x equals, absolute value of x equals 5, at 5 and negative 5. We'll see this when we look at the graph in a minute. So this should be strictly less than. And the derivative here is negative 2, and this is 2. It is defined, everything's defined at 1, so we can take this and find the f of 1, and that is the absolute value of 24 is 24, and then the derivative, that should be the second derivative, the derivative at 1 well, let's see, 1 has an absolute value less than 5, so it's put it in here, so we use this formula and put a 1 1 there, and so that's negative 2. So that allows us to get our formula for the tangent line, y, or t of x, equals, the slope is the negative 2, and then you have x minus the x value of 1, and then plus you have the y value there at 1, which is 24. Okay, so let's graph these. So let's clear this out. Okay, so the original function was, I think we can actually type this in like it originally is with absolute value of 25 minus x squared. Okay, let me okay, so let's see, it doesn't look like it's not going to go into the negatives anywhere. The absolute value on the outside, we know that. First of all, just right off the bat, you notice the sharp corners here at negative 5 and 5. So that's going to be, that's typical when you have absolute value. You have a sharp change of direction, and there's not going to be a derivative at those points. Now, to get a better view of this, though, I'll need to change my grid range a little bit. I don't need to go very far into the negatives on the bottom, so I'm going to go down to negative 2, but I need to go up a ways further. Let's go up 25 and see if that's enough. And what if I just go from negative 10 to 10 on the x's, and let's see what that looks like. That's pretty close to what I want. That's not bad. We could just use that. Actually, I may need to see. We're definitely going to have some negative derivative here and here, so this is probably still not the best window when I start putting the derivative on here. So the derivative is going to have some lines there. So let's see. So I need to change my grid range a little bit more still. So let's go, the negative 10 to 10 is okay, but let's actually go down to, say, negative 30 on the bottom and positive 30 on the top, and let's see what happens there. Alright, so there's our original function. Okay. That's f of x. Okay. Now the derivative. The derivative looks like y equals negative 2x, and this is when the absolute value of x is less than 5. So this is going to be between negative 5 and 5. So I can do it. In Graphmatica, you put a brace, you say x colon, negative 5, comma 5, colon, and you get that part of a graph. Part of the graph of y equals negative 2x. And then you have y equals positive 2x for x with larger absolute value, greater than 5 and less than 5. So I'm going to have to do that as two different graphs here. So I put y equals 2x, and this is from x going from 5 to infinity. And infinity you just leave a blank space in Graphmatica, and we get that. And then for and it's the same formula from forever left up to negative 5, and we get that piece. And that's all one function. They're actually open dots at the ends of each of these pieces. Okay, so we've been drafting the derivatives red, so we'll make all these red. This is one function. I had to enter it as three different functions in Graphmatica, but it's actually one thing, so we're going to make it one thing by making them the same color. And there's open endpoints on both of these. Open endpoint here, arrow on the right. Open endpoint here, arrow on the left. And then the derivative, second derivative then, is y equals 2, and that's going to happen again for the left part, the left piece, which is x is going from negative infinity up to negative 5. And then it's also going to be the same formula on the far right piece, which is x going from 5 to infinity. And in the middle part, the derivative is negative 2, and that's going from negative 5 to 5 for the x's. And those are all the derivative, the second derivative, which I think we've been using purple, so I'll make them all purple. So there's the second derivative. Okay? And then the tangent line at x equals 1, we came up with the formula y equals negative 2, parentheses x minus 1, plus 24. If we did this right, it should touch the graph when x is 1, and the slope should be the same there. It looks, yeah, that looks like a tangent line. That looks good. Let's make the tangent line green, let's say. How about, there we go. And so there we have the functions. So we'll place f of x on that one, that's the blue one. And f prime of x we can put on the red one here. And f double prime we'll say is this purple one here. And the t of x is the tangent line, which is this green one here. So notice that basically what's happening with the absolute value, it gives us a reversal of direction when the normal. So if I just graphed this function inside the absolute value, I'll delete it in a minute, but look what happens here if I graph this without that. You get this shape right here. Okay? But notice the part that's down below the axis gets flipped up above the axis. The part that's above the axis stayed where it was. So what is that going to do? That's going to flip the derivative. So the derivative of this last one I graphed would be this line negative 2x all the way down. But what happens is this part over here gets flipped over. So if we get rid of that and back to the original function, this sharp corner means the derivative is undefined at that point, and there's actually discontinuity in the derivative, which of course means there's a discontinuity in the second derivative as well. The original function is actually continuous, but not differentiable at those 2 points. So, kind of interesting function there. Absolute value definitely has a tendency to stick in those sharp corners, abrupt changes of direction. And that's very typical of an absolute value function. And it's really because it's an absolute value function is really a piecewise defined function. So that's why you see the different pieces here in the derivative and the second derivative. Next function we'll look at is square root of 2 plus e to the pi square.